So yesterday we really practiced this. So you have to know because the directions just say evaluate, and that's not really helpful. What might be helpful would be to say like, oh, find the exponent, which would make this true. You know, like something that would lead your brain into thinking about exponents. But you have to know from this point forward that log means we're talking about exponents. So I think when I read this, I think 13 to what power is 169? And what do you guys come up with? 2. The answer is 2. 13 squared. Oh. So number 1 is 2.
Well, I mean, it's like if this was on the test, like we would have to rewrite it. Like,
no, all you would have to write is 2. No, you really don't. For number 2, I have to think 2 to what power equals 1 over 128. It's negative 6. So 2 to the 6 is 2 to the 7th is 128. So whenever I have a fraction, I just kind of focus on that base and I try to figure out, how to get the number. And then I know if a number turns into a fraction, I'll have to use a negative exponent. So this answer is negative 7. Number 3. 6 to what power is 1? 0. Anything to the 0 power is 1. So that's that. Let's just check your textbook. You got a lot of it done in class by now. You like that? A little more standard speech. Didn't mean to come out that way. Thank you. Thank you. I wasn't here yesterday, but I had the night before homework. Okay, yeah. And I started this one, so I'll finish it soon. Okay. Thank you. Thank you. Does anybody have any specific questions? Would you like to chop my head off? All right. Are there any questions? Okay. Today we're going to practice graphing logarithms. So if you have your own graph paper, you can get it out. If not, just do it in your notebook. All right, so one thing to know is that logarithms have the same shape as exponential curves. So like with the credit card project, an exponential curve started low and went high like that. This is the same shape, it's the same relationship, it's just perfectly inverse. So it's flipped diagonally, so it's kind of going like this. So a log graph has the same curve as an exponential graph. I think out of all of this information, this is right in your textbook. I don't expect you to copy all of this down. I think out of all of the information, what's important is right here. If the base is greater than 1, the shape will go like this. If the base is, it says between 0 and 1 because the base cannot be negative, then it's going to start high and go low. So out of all of the information you're given here, I think that in your notes, if you just want to write b greater than 1 and show this shape, and then b less than 1 and show this shape, it could be helpful. So for like transformations and things, it's really similar. Like if I had a log 3 here, I would start with log base 3 of x in the table, and then if it had like plus or minus anything, I would do extra columns to like move it left, right, up, or down for that vertical and horizontal translation. I think we are going to start with base 30. Okay. What? No, I mean, it's helpful to know that when the base is greater than 1, the picture looks like that. When the base is less than 1, the picture looks like that. But you could throw a negative in there, and that flips it anyway. So. Okay, this is in your book if you want to look at it and look at it somewhere. I'm going to move on. Yeah, let's try log base 3 first. So let's make a table. All right, there's more than one great way to make a table for a log function. One way is to consider beginning with y values instead of x. And also consider the exponential form. So what I'm telling you, this isn't the only strategy, but what I'm telling you is instead of giving x, go ahead and give y. So I'm plugging in y values, -2 through 2. Normally we put in the x column, right? Because it's the independent variable. But this kind of helps with comprehension. So converting this to exponential form, f of x is y. So converting this to exponential form would be to say 3 to the y equals x. Because it's base to the power equals the argument. So really, I'm going to use 3 to the y equals x, which is like the converted form. So over here, I would do 3 to the -2, 3 to the -1, 3 to the 0, 3 to the first, and 3 squared. And that's not necessary if you have the insight to just know what powers of 3 would be. So, I mean, I could teach this two ways. I could say, go ahead and plug powers of 3 in for x. Or I could say you could always use these y's and go backwards. Yes?
So is this function just like a rotated exponential function?
It's a perfect inverse. So if you remember inverses, we switch x and y. Like the definition of inverse is switch x and y. It's perfect inverse, and it reflects diagonally. So like tomorrow, I'm going to have you graph 2 to the x, find the inverse, which will be a log, and graph that in the same coordinate plane. Okay, so then our x would be 1/9, 1/3, 1, 3, and 9. And those are our ordered pairs. All right, so x is 1/9 when y is -2. So here's what that looks like. So here's 1. So 1/9 is like 0.1, and y is -2 is right here. X is 1/3 when y is -1. X is 1 and y is 0. X is 3 and y is 1. X is 9 and y is 2. It doesn't go negative. because it's impossible to get a negative x value in this equation. So domain and range. No. It's not. X will always be greater than 0. But the y value will be all real numbers. So the domain and range from the exponential graph switched because all the x's and y's perfectly switched. You can. You can always start with these y values for a log function. Consider that. You might just get to a place where you don't need to because you can like see in your log argument like what you want there would be powers of 3. Work backwards. Yes.
So what's the domain and range? Can we say the domain is anything above 0 and the range is all real numbers?
Mhm. Let's try another one, a little more difficult. Okay, so so that's y equals log 1/4 of x. And now I'm going to convert to 1/4 y equals x. Use the same y value. Shaboom. Everything switched. So 1/4 -2, the reciprocal will be 4 squared, which is 16. even why we get it. Here we go. Okay. So we were at 16 positive 2. 4, nope, 16 negative 2. 4 negative 1, 0. 1 4, 1, 116, 2. This is the inverse of a decay function. We talked about exponential growth and exponential decay. Well, that's the inverse of a decay. Okay, we're going to do one more of a transformation. But I can wait. Okay, here's our transformations. It literally says everything that every transformation has always said. And you guys are getting really good at this now. We've been graphing transformations pretty much since absolute value function. So A would be a reflection. A stretch or a compression. Any value in parentheses with X is a horizontal translation. And any value at the end is a vertical translation. Let's just do one before.
Oh. Yeah, for one second.
Yeah. Okay.
What is orientation and shape?
Stretch and compression, like is it steeper or lighter, or is it reflected? So for this, we're going to begin with log base 5 of x. So kind of ignore the 4 and the minus 5 and do your parent function table. This would be like the parent function of base 5. Our table's probably going to go up to 25, so we might label our axes a little different. So same idea, -2, -1, 0, 1, and 2. But I'm going to consider from here 5 to the y equals x. So 5 to the -2, 5 to the -1, 5 to the 0, 5 to the 1, and 5 squared. So that's the main one. That's the base. Alexis, what do you think this 4 is going to do to these numbers? So I'm going to extend this table. And now I'm going to go right 4, which means I add 4 to each of these. And so like we've done in the past, you are allowed to use a mixed number. So 4 plus 1/25 is 4 and 1/25. 4 plus 1/5 is 4 and 1/5. Yeah. The parentheses and the -4 here. And then also I'm going to do another one here because this -5 means it's going to go down 5. So this equation is log base 5 of x, but it's going to be translated right 4 because of the 4 in the parentheses and down 5 because of the 5 at the end. So yeah, -2 minus 5, -7, -6, -5, -4, and -3. It's the outside columns that will graph the transformations. But it's nice to graph, you know, the inside and the outside. Really shows the transformations. Do you have to graph the parent function? No. You can get 4 points. 4 points is enough. Nope. X is 1/25 and y is -2. Right there. Okay, so this is just y equals log base 5 of x. And now the outside ones. Go here. Paige, is your question coming true? No, no. So your question is K a y-intercept? No. It's way down here. That was the answer. So this is the transformations. One thing that's like essential to getting full points on this graph is that this P graph cannot go beyond 4. You have to flatten it out correctly. So the domain of the domain of the transformed is x is greater than 4, which comes directly from this h value here. And the range is still all real numbers. So the shift right for is probably the most important part, is that you understand that this is pretty flat here. It gets really flat, but it doesn't cross. I recommend it, like, because you're already making, you're already making the table. It's good for practice, good for accuracy, good for understanding. Do you have a question on it? Okay. Yes, it is. Yes, it is. This, for log equations, for our purposes, is always all real numbers. And the domain will be whatever number's in there. So you just have 2 homework problems, 17 and 18. So I can get started on them with you. In the workbook,